Good morning, everyone. So I have here the results of the test up to this point. So we still have a few students who had something come up and had to delay the test. So, but this is the majority of the class right here. So from the results, you can see the orange here. So these are each student in the class. And you can see they're arranged in order, so highest to lowest. The orange is exam 2. The blue is that student's grade on exam 1. So for example, this particular student got a 94 on this test, got an 86 on the first test. So their grade went up a little bit. So you can just kind of see how the class did here. The number of A's, the number of B's, C's, D's, and F's on the exams. The blue one is exam 1, orange one is exam 2. So the number of A's went down a little bit. Number of B's was the same. C's went up a little bit, D's went up a little bit, F stayed the same. The average on the test was an 83. The average on the first test was an 89, almost a 90. So the average went down a little bit. And yeah, but overall, anytime I have this many A's and B's, I'm pretty happy about things. So, you know, if you haven't not done well on the first 2 exams, you know, just get with me if you want to during my office hours. We can talk about, you know, where to go from here. Yeah, any questions? We're good. Okay, all right, we are going to get into some new material today. And on our schedule, what we're looking at is this. Again, we're doing things in a different order, but we're doing polynomial functions today and their graphs. And then we'll try and get into rational functions. It depends on how far we get, but we're going to be talking about polynomial functions. So just as a recap, you know, if you look at what we've done in this class so far in terms of graphing functions, we really have done 2 things. So I'm saying recall here. Recall. We know how to sketch lines and parabolas. That's what we know how to do so far. So for example, if we wanted to do a line, we would have to understand that all equations of lines can be written as y equals mx plus b, or if you don't want to use the y and treat it as a function, then we can write f of x equals mx plus b. But either way, the m was the slope of the line and the b was the y-intercept, and then we graphed the lines. And you had to do that on this test, right? So we should be somewhat comfortable with how to do that. The other thing that we know how to graph is parabola. And this was a whole set of steps that I gave you, right? We have to figure out if it opens up or down, find the vertex. There was a formula for that, and then do all the steps, right? So parabolas look like this: y equals ax squared plus bx plus c. Or again, if you want to change the y to f of x and look at it as a function, it looked like this. Right? So we should be somewhat comfortable with this. Would you all agree? We've done this, we've been tested on it, we've got these kind of down. The steps for doing these are different, right? The process for graphing a line is completely different than the process for graphing a parabola. So now what we're going to do is we're going to try and see if we can come up with a way of graphing what are called polynomial functions. And polynomial functions have their own steps. So it's a whole new set of steps for this new type of function. So what we need to start with is, what is a polynomial function, right? What do they look like? We know lines look like this and parabolas look like this, but what do polynomials look like? What do their graphs look like? And then from there, we'll get a set of steps. So what are polynomial functions? I should also mention that when we were graphing lines, we did some word problems where it made sense to use a line for like the cost of something when we did electricity, like on the test. Y'all did real good on that question, by the way. And then parabolas, I told you a bunch. Remember that day I was way off? I was all delirious. I was talking about parabolas and satellites and, you know, launching lobbing projectiles into a castle like that. We talk about all these different things that parabolas are used for in the real world. Polynomial functions, they look different. They're not lines, they're not parabolas. So, you know, what are they, right? So I'm going to first start with what they look like visually. All right, so when you look at them, what do they look like? Well, polynomial functions, when you graph them, they're going to look like this. It's going to start out on the left-hand side. It's going to, you know, maybe go up and then down and then back up, something like that. That's one example of a polynomial. Not every polynomial looks like that. You could have something like this. Okay. The way you can look at it is a polynomial is basically like this, almost like a roller coaster. Okay, it's just kind of curved, it's kind of going up and down. And so notice that on the left end and the right end of these two functions, or on this first one. On this first one, do you all see how the left side goes down and the right side goes up on the end, right? And then on this one, do you notice how the left side goes up and the right side goes down? We call that the end behavior. The end behavior of the polynomial. Okay, end behaviors is what's happening at the ends. And so from the graphs I've given you, it looks like you can have the left side go down, the right side go up. You can have the left side go up or the right side go down. And in the middle, it's just this wavy looking function, all right? And how many times it goes up and down really just depends, all right? Now we can also have, the left side go up. It can wiggle around here, and then the right side could also go up, right? So we could have that also. And then lastly, we could have it where the left side goes down, wiggles around, and then the right side goes down. So there's really, when you look at polynomials, there's only really four things that can happen in terms of the end behavior. You can have both sides go up, both sides go down. You could have left side go up, right side go down, or left side go down, right side go up. So that's it. Those are the only things that can happen. And what our goal is going to be is to figure out what this wiggling thing in the middle looks like. Okay, the end behavior is once I show you, is going to be easy for us to determine. It'll be easy for us to figure out if both sides go up or down, or the left side's down or up. That'll be easy. The hard part is going to be trying to figure out what the middle of this thing looks like. Okay. So if we were to try and describe what a polynomial is, a polynomial function when we look at it, polynomial is smooth and curved. Okay, so if you were to draw these, would you agree that these curves look smooth and these look, excuse me, look smooth and curved, right? There's no straight lines here, right? There's no jagged edges. Like, I'm not drawing this. I didn't draw this. Right? See all these sharp corners? Okay, that's not what's happening here. They're smooth and curved. All polynomials are, I should have said. Polynomials are smooth and curved. all right? So that's going to help because when we draw them, we want to make sure we don't put any sharp corners or anything like that. Now, can anyone think of anywhere in the real world where a polynomial function might like come into play? Like something that behaves like that? Go ahead, Angelique.
Maybe like with like a business, like the income or like.
Sure, yeah. Think about, you know, you have maybe you run a company or something and you're looking at how much money's coming in, right? It'll fluctuate. It'll go up and down, up and down. Temperature, right? Think about the temperature outside every day. It goes up and down. And think about the aquifer, right? How much water's in the aquifer? They measure it every, you know, they're constantly measuring it. It fluctuates, right? So polynomial functions, they are useful because they're kind of all over the place. And so again, in math, what we're doing is we're trying to understand functions so that we can model things that happen in the real world. All we want to do in this class is just kind of know that they exist, know what they generally look like, and then be able to sketch them. Well, they can be very complicated. Okay, so we're going to kind of only focus on kind of basic polynomial functions. We're not going to get too crazy here. Now, when you look at these, where we have these little like wiggles, these up and downs, do you see that these points right here would be like the peaks and the valleys of the polynomial, right? Those would be like your highest and lowest points, right? These peaks and valleys. And in the real world, it's actually important for us to be able to find those peaks and valleys. And so I'm here to tell you that in this class, we will not be trying to do that, okay? All we will do is figure out, you know, whether or not it wiggles up and down. We won't be able to say how high or how low it goes. And it turns out that in order to answer that question, you have to take calculus. In calculus, that's where you figure out how high and low these things go. So when you think back to a parabola, remember all parabolas had to either go like this or like this. And we had this very important point called the vertex. We were able to find that point, weren't we? I gave you a formula for it, HK. That formula actually comes from calculus. So in calculus, we actually find a formula for it. And then we let the algebra people use it, right? So just so you realize, we could do this. We could find the highest and lowest point on a parabola, but that's it. Once we get to the general polynomial, we have to kind of wave our hand and say, no, that's too hard for us to do here. And even in calculus, there's not a general formula. There's more of a process you go through to find those highest and lowest points. So, all right. So now that you know kind of what they look like visually, and we have this idea of end behavior and these wiggles, then we need to know what they look like when you write them down algebraically. Like we know what a line looks like, mx plus b. We know what a parabola looks like, ax squared plus bx plus c. So let me show you what a polynomial looks like when you write it down as a function. So a polynomial function looks like this. It's a function, f of x. And then what you have is some number. Okay, so remember with the parabola, it was ax squared plus bx plus c. Remember that? That was parabola, right? That was our quadratic. So with a polynomial, we'll have a, right? Just like we did here, we'll have a number in front of x, but the power on that x can be any power, all right? It doesn't have to be squared or cubed or fourth power or fifth power. It can be any power. So I'm going to call it n. And then I add to that some other number, just like I did with the b in front of the x. And that x here, all I can tell you is that that power is different than this power, right? So just like this was x squared, the next one was x to the first power. Notice this power is one less than that power, right? So this next one, I'm going to put x to the n, take away 1. So whatever this is, this will be one less power. So if this was a 5, this one would be 4. If this was a 10, this one would be 9. And I keep doing this. And I keep reducing the power by 1 each time. And I keep doing this all the way until I get to the very end. And at the very end, I should have some number. All right, just like this C by itself. But I can't use C because I've already used C, right? I have A, I have B, I have C. So I'm just going to put here for a number, why don't I put K, all right? And this is just a number. Now, there's a couple of things that we need to know about a polynomial function, some language. First thing is this n right here, that n, that is the highest power of x. That we see. So the highest power of x that you see in there is called the degree of the polynomial. And the number in front of it, just the number in front, is called the leading coefficient. All right. Now, there are some restrictions when it comes to polynomials about these powers, right? Just like the parabola, you know, we had x squared, x to the first. Here I told you n can be anything, right? It can be any power, but there are some restrictions. We have this, n must be a non-negative integer. Now, what do I mean by non-negative integer? I mean, it can be 0, it can be 1, it can be 2, it can be 3, it can be 4, it can be 5, it can be any of your natural counting numbers, all right? That's what you need in order for this to be a polynomial. Those have to be nice numbers. You cannot have fractions as a power. You cannot have decimals as, negative numbers as a power. So they have to be 0, 1, 2, 3, 4, 5, you know, however high you want to go, you can go. All right. So that's the general idea here of a polynomial. Let me give you some specific examples. All right. So as examples, let's look at our first one here. F of x equals, let's go with 3x to the 4th minus 12x squared. Okay, this is a polynomial function. The reason it's a polynomial function is because I see two terms, right? Terms are separated by addition and subtraction. So I have one term here and a second term here. When I look at both of these terms, I have a number in front of x to a power, right? A number in front of x to a power. That's all you need in order to have a polynomial. It's just a bunch of things put together with pluses and minuses where you have a number in front of x to some power. The highest power that I see here is 4, right? That's the highest power I see. So I could say for this, that the degree of this polynomial is 4. And then what about the leading coefficient? I'm going to call it leading coefficient. I'm going to call it LC from now on because I don't like to write that over and over. So what would the leading coefficient of this one be?
3.
3. It's the number in front, right? So the leading coefficient is 3. That's this number right here. Okay, so degree was 4, leading coefficient was 3. Now you might be asking, well, wait a minute, what about it's missing the x cubed, right? Like there's no x cubed in here, and there's no x, and there's no number by itself. You understand what I'm saying? Like it seems like it has gaps. Well, here's the thing. You could, if you want to, you don't need to do this, but you could rewrite this as 3x to the 4th plus no x cubes minus 12x squared plus no x's plus nothing at the end. Do you see how this, everything I'm going to underline here in gray, these are all actually not there, right? They're all gone because they're zeros, so they're not there. But if you look at it this way, you do have numbers in front of x's to every power of x from 4 all the way down. Number, x squared, number, x, number by itself. Now you don't need to write this, but I'm just trying to show you why this falls into this right here, this general form, is you do have numbers in front of all these different powers of x. Just sometimes these numbers right here can be zeros. Does that make sense, everyone? Do you have any questions on that? Okay, let's look at another example. Let's see here. Let's go with, okay, negative 2x squared, no, cubed, sorry. Trying to make something that works here. Plus 4x squared minus, no, make it plus 4x. There we go. Okay. Is this a polynomial function? Yeah, right. You have a bunch of terms, right? Each of them is a number in front of x to a power. So what would the degree of this one be?
Would it be 3? 3.
That's the highest power of x we have, right? And what would the leading coefficient here be?
4. Negative 2.
Negative 2 would
yeah.
be the number in front of that highest power of x. So it'd be negative 2 here. Do another one. F of x equals, let's go with x to the third minus minus 5x to the fourth. So what about this? We have numbers in front of x's, and those x's are raised to powers. Those powers we see are nice counting numbers, right? They're not negative, they're not fractions. So what would the degree of this one be? For Amira? Amira, hold on, I'm saying that wrong. Amira, right? Yeah, Amira is saying 4. Do you all agree? Is that the highest power you see? Yeah,
yes.
Right. So I didn't put it in the right, it's not the first thing you see, it's the highest power you see. So the degree of this would be 4. And then the leading coefficient would be the number in front of that highest power, which would be negative 5. Okay, so you do have to pay attention that, you're not just always looking at that first term. You're looking through the whole thing and you're trying to identify where the highest power is and then the number in front of it. Okay, questions? Do you think you have a general kind of idea of what a polynomial looks like, how to identify its degree and leading coefficient? That makes sense?
So if it were to be in that order, can we put it in the correct order or it has to
Sure.
stay the way? Okay.
Nope, you could change it. If you didn't like the way this looked, you just have to make sure you do it correctly. So you could rearrange this. You'd put the negative 5x to the fourth here, and you just have to put a plus x cubed because it's positive.
Okay.
And that would be the same thing.
All right. Thank you.
Yep.
I had a question about the leading coefficient.
Mhm.
So it's not the highest number, correct?
No, it's not the highest number. It's the number in front of the highest power of x. So once you identify the degree, right, then you just look at the number out in front of that.
Oh, okay. I'm sorry, I missed that.
Oh, no,
Thank you.
good. I'm glad you're asking. You identify the degree here, x cubed, right, is 3, and then you say, oh, what's the number in front of it? Negative 2.
Okay.
I think what you were asking is the leading coefficient the biggest number that you see, right?
Yeah, I couldn't figure out what was, when I was taking down my notes, I think I wrote it wrong.
Okay, yeah, it's always just the number in front of that highest power of x.
Okay,
Now, I told you a minute ago that when it comes to polynomials, they all kind of look like this. And then when it comes to the end behavior, that there's only 4 possibilities, right? Left side down, right side up, left side up, right side down, left up, left down, right down, right? That's the only 4 things that can happen. Well, it turns out that the degree and the leading coefficient, if you can tell me what those are, you will be able to then tell me exactly what happens at the end. And to do that, you use what's called the leading coefficient test. So I'm going to put this down. It's going to be very important. You're going to probably want to copy this and put it on your reference cheat sheet for the next test. This is going to be what's called the leading coefficient test. Now, what I'm going to refer to this as LCT from here on out, okay? LCT, leading coefficient test. What this test does is it tells you the end behavior of the polynomial function. Okay, it tells you what the end behavior is. So I told you there's only 4 possibilities, right? There's only 4 possible outcomes. So what I'm going to do is I'm going to make a table. So this is the part that's important. I'm going to make a table. Okay, now I'm going to put in this table the kind of 4 different scenarios we can get. So think about when I was asking you for the degree. When I ask you for the degree, would you all agree that the degree has to be some number from this list, right? It's either 0, 1, 2, 3, 4, 5, 6. So the degree will always be the highest power of X. When you look at that degree, that number is either going to be even or odd, right? It's even or odd. And that actually tells you something. So I'm going to put over here n even and odd. Those are the two different things that can happen. Remember, n is the highest power, right? N is the highest power. So n can be even or n can be odd. And then when you look at the leading coefficient, right, the number in front, that number can either be positive or negative, right? It's either going to be a positive or a negative number. So on here, I'm going to put LC positive, LC negative. In each of these boxes here that are remaining, you can close this off if you want. You don't have to. In each of these boxes that's remaining, I'm going to tell you what the end behavior is going to be. So I'm going to put this first box here. I'm going to put up on the left, up on the right, and in the middle, I want you to put a question mark. So what this means is that if you have an even leading coefficient and you have a positive, sorry, I meant to say an even degree. If your degree is even, your highest power of X is even, and your leading coefficient is positive, then you will be looking into this box, and that means both sides go up. Does that make sense the way that table works? Now, if you have an even and your leading coefficient is negative, then what's going to happen is your left side is going to go down and your right side is going to go down, and in the middle we kind of don't know. The question mark is because these things wiggle around, right? So we don't really know yet what the middle looks like, but I can tell you what the ends look like. Then if you have an odd degree and a positive leading coefficient, your left side will go down, your right side will go up, and the middle will be a question. And then this last one is left side goes up, right side goes down, question. Now, we're not going to get into why here, okay? We're just going to take this and be like, okay, if we see this, this is what happens, and I believe you, right? That's basically what we're going to do. All right. So let's go back up here and let's look at these examples that I just gave you. Look at this first one. Can we figure out the end behavior? The degree here is what? What are we looking for? When it comes to degree, we're looking for whether or not it's what?
Even or odd.
Even or odd. So here, 4 is even, right? That's an even number. The even numbers 2, 4, 6, 8, 10, 12, 14, 16, right? The odds are all the other ones. 1, 3, 5, 7, 9. So we know I have an even degree, and then the leading coefficient, what we're interested in here with the leading coefficient is whether or not it's positive or negative. And in this case, it's positive, right? So if we have an even degree and a positive leading coefficient, even degree, positive leading coefficient, here's what I can tell you. Left goes up, right goes up, in the middle, I don't know. Does that make sense how that works? The next one, my degree here, 3 is odd, and my leading coefficient is negative. So if I come to my table, odd degree, leading coefficient negative, we have to be looking here. So that means my left side goes up, my right side goes down, and in the middle, I don't know. And then the last one, we have an even degree, and we have a negative leading coefficient, -5. So even degree and negative leading coefficient, both sides should go down. What do y'all think of that? Do y'all think that that is going to be kind of an easier part of this, this whole graphing thing? Just looking at the degree and leading coefficient and using the table? Most students are like, hey, let's just do 100 of those problems on the next test and I'll be happy, right? Okay, that's the easy part. The hard part is figuring out the wiggles, all right? That's the really hard part. So let's go try and now talk about how we're gonna do it, all right? This is the first part of how, I have not given you the steps on how to graph these yet. I'm building up to it, okay? So now let's go back and take a look at these graphs. And let's notice something about these graphs. They have on them these points where the graph would cross the x-axis or touch the x-axis, right? We call those x-intercepts, don't we? All of these graphs have x-intercepts. And it would be useful to us if we knew where they were, because it would help us get a good picture, a better picture of what's happening, right? We would know what the ends are doing. We would know where the actual graph hits the x-axis. That should help us draw a picture. So we need to go find the x-intercepts. That will be the next thing, all right? We've got the left and right behavior down. Now our next thing is to talk about the x-intercepts of a polynomial function. So the way we find the x-intercepts of any function is you will set the function equal to 0 and solve. Okay, and I'm just going to tell you right here, this is the hard part. In general, this is very difficult. So like, remember at the beginning of this class, I told you that we have 2 college algebra classes, 1314 and 1414. And you all are in this class, right? So this part right here, I'm going to make sure I make these polynomials doable, okay? In 1414, I actually started this section yesterday with my 1414 class, and we are already, you know, suffering in there because the problems that we're getting are difficult. is we're having to learn like new techniques to solve equations. And so I just want you to know this is the hardest part, but within this class, we're going to keep it like, we're going to play nice, okay? So all we need to do is solve an equation, right? That's basically it. So let's do an example, all right? Let's do an example. Let's find the x-intercepts of the function f of x. And let's go back to the one that we've been working at. Let's do that first one right here. This one right here, 3x to the 4th minus 12x squared. 3x to the 4th minus 12x squared. Okay, so if we want to find the x-intercepts of this, according to what I said here, we just need to take the function, set it equal to 0. So I'm going to take 3x to the 4th minus 12x squared, set that equal to 0 and solve. Here's where we do not have a quadratic formula now, right? Remember how we used the quadratic formula? Yes, here we don't have it because this is not a quadratic. So it's your ability to do this is going to be solely related to your ability to factor. And I realize that this is going to be a weakness for some of you. And that's why I'm going to keep these problems all kind of within a certain scope of difficulty. So I do expect that everyone here can do GCF, greatest common factor. So you should be able to look at this and you should be able to say, oh, there's something that these both have in common. Can someone tell me what they both have in common?
3 and x squared.
3 and x squared. So I can factor 3x squared out. If I do that, what would still be in this parentheses? So I always ask myself, like, what would I have to multiply this by, 3x squared, to get that? So what am I missing? I have a 3, right? I have 2 x's, but I need 4. So I'm missing how many?
X squared.
2 of them, right? X squared, right? So I need an x squared there. Okay, great. And now I play the same game and I say, okay, what do I need to multiply this by in order to get this?
4.
-4.
-4.
-4. Good. -4. Now, if you're unsure whether or not that worked, you can always distribute this through. And if you distribute, you should get this back. All right. That is our first step. Let's pull that GCF. So from here to here, I did GCF. Now at this point, you want to look at what's left and see if you can continue to factor. So do you all recognize something here? I know some of you do. Recognize that? What is x squared minus 4 called?
Wouldn't that be x plus 2, x minus 2?
Yes, that is x plus 2 in parentheses times x minus 2. We call this a difference of squares. And that, again, is something I'm going to expect that everyone here will recognize. Something squared minus something squared breaks down to be this. If you want to recall, there's a formula for this. A squared minus b squared equals a plus b times a minus b. That's your formula. Are there any questions? I'm about to break this down. Any questions? Plus 2x minus 2 equals 0. Now at this point, I can't do any more factoring, right? There's nothing else to break down. X minus 2, x plus 2, 3x squared, can't break that down. So what you do next is, since this is multiplication between these, you will set each of the factors equal to 0, just like you did with the parabola. Set that to 0, set the next one to 0, set the next one to 0. When you solve these, well, these two should be straightforward. Just here, you move the 2 to the other side, becomes x equals -2. This one, you move the 2 to the other side, so you add 2, so you just get 2. This one, you can do algebra, but you can also just think about it. You know, what squared times 3 will give you 0? What's the only number that this would work in here? What number? No, yes.
Is it 0?
Just 0, right? 0 is the only number you're ever going to be able to square and then multiply times 3 and still get 0. Now, if you don't like that, you can just divide both sides by 3 and you get x squared is 0. And then maybe it's more obvious then, you know, like what number do you square to get 0? Well, 0 itself, so you get 0. Okay, are y'all with me? Now, let's try and again, I have not given you the set of steps yet, right? I have not given you the set of steps. I'm just trying to build up to it by kind of taking each piece of the steps and doing them individually. Right now, if we had to try and graph this, right? If we did, here's what we would know. We would know that when you graph it, you have an x-intercept at 0, you have an x-intercept at 2, and you have an x-intercept at -2, right? That you would know. Agreed? You would also know the end behavior, wouldn't you? Don't you know the end behavior? We did this problem, right? This problem right here, when we talked about the end behavior, we said it would go up, up, right? Up, up. And if we look at it again, coming back here, you know, we have 4, that's even. You've got 3, that's positive. You go to your little table, we have up, up, right? So if I were to try and graph this, since this point right here is the furthest point that I have to the left, what I know is that this graph would have to go up from here. So as I draw it to the left, it would have to go up. And then over somewhere to the right of this, it has to go up also. Right, that's kind of what we know so far, right? Agreed? Yeah, y'all agree? Now, let's try and imagine what it does. I mean, we're kind of guessing here, but would this be okay? Could it do this? Oh, oops. I didn't mean to do all that. Here, let me try it again. Would that be okay? It goes up on both sides and I go through those x-intercepts. Would that work or no? I'm seeing some looks of skeptical looks here.
I want to say yes.
Okay.
I don't know.
Let me ask you something. What is this? What is that right there?
An x-intercept.
That's an x-intercept. Wait, hold on. Didn't we already find the x-intercepts? Weren't they only right there at those 3 points? So didn't I just make up an x-intercept that wasn't there? Shit, something's wrong then, right? Okay, let me rethink this again. This side has to go up. Both sides go up, but I have to have these x-intercepts. How can I draw this then? See, if I try and draw this here, and I do this, the problem is I have to stay, I can't go down here. Do y'all see that? I can't go across the x-axis. Like this is not okay because then I have to turn back up, right? And if I turn back up, I've got to cross the x-axis somewhere. Do y'all understand what I'm saying?
So it just curve at 0 and then go up at 2?
Yeah, so maybe it does this. I don't know if this is what you mean, but maybe it does this. Maybe it touches, just touches, and then goes back up. That would work, right?
Yeah.
That would work because I still have the 3 x-intercepts. My left and right hand sides go up, and that seems to be okay. But the problem with that is that's not the only way it could have happened.
Yeah.
So let me show you a different scenario. Let me take this and copy it. A different scenario that I could have had and still satisfy the conditions that we have is this. Watch. what if I did this? Go through here, come up here, just touch there, come back down, and then go up like that. Wouldn't that work also? See, I crossed through here. I crossed through here. Here at this one, I didn't really cross through. What I did is I came up to the x-axis and I just kind of like bounced off of it, right? Almost like a wall. The graph hit it and came back down. Do y'all understand what I'm saying? Just kind of a bouncing action instead of at these 2 points where it like actually crossed through the x-axis. So is it this picture or is it this picture? Or is there another way I could draw it? I think there's another way. Hold on, let me see. Could I do this? Could I have bounced off the first one, then crossed through and then crossed through and gone? Could I have done that? Yeah, right? Shit, right? So we could have done this too, watch. Won't be here all day. I could have done this. How about bounced off? Oh, I don't mean to make it look so jagged. Bounce off, bounce off, bounce off again. That has the same x-intercepts, left and right hand side goes up. Do y'all see what I'm trying to illustrate to you right now is that having the left and right go up and having the 3 x-intercepts is helpful, but it's not everything we need. To graph this, there's still too many variations of what it could be. I don't have enough information to be able to say which of these it is. Understand? Yeah. So this isn't enough. So there's one more thing we need, just one more thing in order to graph these and get a decent graph. We need, so let me put here, we don't know which of these it is, so we need more information. And that leads us to the last thing called the multiplicity of the polynomial function. So each x-intercept we have comes from some factor. What do I mean? Okay, let me get back to the problem we were working here. When we were doing this step, where is it? Right here. Okay, when we were right here, I'm going to copy this right here. When we were at this step, what I'm saying here is that each of these x-intercepts, 0, right, comes from some factor. It came from this thing, right? That's where it came from, setting that equal to 0. This one comes from this factor, right? This one comes from this factor. Got it? So the x-intercept, these are the x-intercepts. And these are the factors. Understand the difference between the two? Factor, factor, factor. Factor means when we broke it apart, each of those pieces was called a factor, right? We take each factor, set it equal to 0, we get an x-intercept. So in order to determine what this graph's going to look at, what we're going to do is we're going to go back and we're going to look at the power on each of the factors. So we look at the power on each factor. So for the x-intercept 0, if we go back and look here, this x was being squared, wasn't it? Being squared, right? So the power would be 2. With me? If we look at x equals -2 and we look at the power on that factor, It's this x plus 2 is raised to the first power. We don't normally put the 1 there, but everyone understand that that's what it means, x plus 2 in parentheses to the first power. That right there is the power of the factor 1. And then on the last one, again, because it's not written, there's really a 1 here. And so the power on that factor is 1 also, all right? That power on the factor is called the multiplicity, okay? So we're gonna look at the power on each factor, right? The power is called the multiplicity of the X-intercept. Now, if the multiplicity is odd, we cross the x-axis. If the multiplicity, I'm just going to put mult, is even, we bounce off the x-axis. Okay, that's the big thing right there. The power on the factor tells you everything you need to know about whether or not you cross at that point or you bounce off like a wall. All right. So when I go back and look at this problem, right, we had drawn this picture. Let me go back to the picture we had here. Where was our, there we go. Let me grab this one. This was the first picture that we drew, but I hopefully convinced you that we don't know which picture it is. So here's where we're sitting, right? We have this, right? We know our end behavior. We know our x-intercepts. Now what I'm going to do is talk about the multiplicity. At x equals 0, the multiplicity of this is 2 because there's a 2 on this factor. Since 2 is an even number, I should bounce off when I get to 0. So when I get to this, I should bounce off the x-axis. At -2, my multiplicity is 1, and so I should cross through the x-axis because if it's an odd number, I cross. So I should cross here. And then with this one, again, the multiplicity is 1, and so I should cross there because it's odd. Just be careful. You're not, when you're talking about the bouncing and crossing, you're not looking at the number itself. You're not looking at 0 or -2 or 2. You're not looking at that. You're looking at the power of the factor. That's what you're looking at. So now when I go to draw this, I need to kind of have this information as I draw. And I'm thinking to myself, okay, as I draw this down here, when I get to -2, I need to cross through. So let me do that. I'm going to start drawing. I'm going to cross through the x-axis. All right. Now I'm going to try and connect it to this dot. And when I get to that, that's my 0 x-intercept. I should bounce off there. So I'm going to draw it here. I'm going to bounce off and then come back down. And then I'm going to go to 2. And when I get to 2, I should cross through. And you can see here, I cross through. And you know, I'm just going to go like that. I'm going to erase that. I'm going to come back here and erase that and just make it go up like that. There we go. I'm done. That's my picture. It's a lot, isn't it? I mean, this is a lot. We've been here for what, an hour almost, and we basically have done like just built up to one problem here. So let me go to the computer. I'm going to have the computer graph this for us. I just want you to see that what we did matches up with what a computer would give us. 3x and 4 minus 12x squared. So 3x to the 4th minus 12x squared Okay, there's the picture from a website if I graph that function. Is this what ours looks like? Well, I'd have to zoom out a little bit, right? Does ours behave this way? Let me adjust it a little bit. Let me go. I would argue that ours does not look exactly like this, right? We have those same x-intercepts? 0, -2, and 2. Is that what we have? Yeah. Does our left side and right side go up? Yes. Okay. When you are looking between -2 and 0, does our graph go below the x-axis? Does it go below? When you're looking between, wait, this was not my picture. Where was my picture? Here we go. Here was my picture. So do we go below and then come back and bounce off? We do, right? So our picture is not perfect, but it's good enough, all right? So everyone's picture is going to be slightly different, right? Everyone's going to, if I ask you all to graph these, everyone's picture will look a little bit different because how far you go down is completely up to you. Like somebody else could draw me this picture and it could look like this. And that would be full credit. You would get 100% on that answer because we are not concerned in this class about how far this dips down or this dips down. What I want to know is, can we find the end behavior? Can we find the x-intercepts, and can you determine if it bounces or crosses? When you get to a calculus class, which I know most of you are not doing, in calculus, that's when we say, well, you better get this part right too, because now I want to know how low it goes and how high it goes. Make sense? Okay. So let me put the steps down and then let's do one from start to finish. Okay, here we go. So the steps. Steps to sketch a Poly function. When I write them down, it's going to seem so straightforward and easy because there aren't really a lot of steps. The first step, leading coefficient test to get your end behavior, which y'all said, or I guess no one disagreed with me when I said that that's pretty easy, this step. You just figure out which, in that table, which of the cases it is. The second step, the x-intercepts. And that's where we set the function equal to 0. That is going to be the hard part. I already said that. The third step is going to be the multiplicities. That will tell you whether or not you cross or bounce at the x-intercepts. And then the fourth step is to draw it. That's it. It's actually less steps than the quadratic. Remember the quadratic? Quadratic was like, does it open up or down? Vertex, so you have to find H and K. Quick sketch, do you have x-intercepts? Go find the x-intercepts. Y-intercepts, sketch. So there are actually 6 steps for parabolas. There's fewer steps with polynomials, but it's harder. All right, here we go. I'm going to let you just see how much you can do over the next, let's 5 minutes, because I do want to be able to finish this problem on, in the time we still have left. So why don't you take 5 minutes and just see how far you can go with this, all right? Do you want me to put the table up here for y'all? Would that help to have this up? I can put it here just in case you don't have it. Put it right here. There we go. I will also put that whole thing I did about the multiplicity. Where did I put that? There we go. Probably getting mad. Stop moving things around. Okay, that should be good. All right, see how you do in the next 5 minutes. Let me give you about 1 more minute. Okay, I think we're ready to go with this one. How'd y'all feel about this? How about end behavior? Who got my end behavior for me?
It should be the first part goes down, the second part goes up.
Good. Okay, so should be that because the degree of the polynomial is 5, right? Highest power of x. And the leading coefficient is the number in front, which is a 1 because we don't have anything written. So it's implied that there's 1. So you have an odd degree and you have a positive leading coefficient, which puts us into, sorry, that's the wrong one. Puts us into here. Is that all okay with everyone? So our first step, we got. Second step, I'm going to need to write it down. So second step is to set the function equal to 0. This is the hard part. So anyone want to tell me what they did here first?
So I factored it by taking out x to the third power.
Okay, good.
And then in parentheses, I had x squared plus 2x plus 1.
Good. So that's a GCF coming out. And this is the part I was curious how people would handle this. This is not a difference of squares. This is a quadratic trinomial. We need to see how to factor that. So on the side here, let me just clarify how we've done this in the past. What we did is we took the number in the front, 1, and multiplied it times the number in the back, that's 1. And then we take the number in the middle, that's 2, and we try and come up with 2 numbers that multiply to be this and add up to be this. And those 2 numbers are what? What 2 numbers multiply to be 1 but add up to be 2?
1.
1 and 1, right? So 1 and 1. If you take those 2 numbers and multiply them, you get 1. If you add them, you get 2. So what that allows me to do now is take this and break it down into 2 factors. It'll be x, and then I put the first number plus 1. And then I put x, and I put the other number, which is also plus 1.
So that's where I got stuck because that would give 2 of the x-intercepts both as -1.
Exactly. Okay, so let's see what's going on here. This turns into x cubed times x plus 1 times x plus 1 again equals 0. Are we all good up to this? Any questions? So this is where I told you you're supposed to set each of these equal to 0, right? And I think Emily's saying that, well, you know, you have 2, you have the same x-intercept twice, right? -1 and -1. So what I'm going to do instead is I'm going to rewrite this as x plus 1 squared equals 0. That's kind of a key tricky part of this problem, because x plus 1 times x plus 1, that could be rewritten as x plus 1 squared. That's what it means, right? And now when you set each of these factors equal to 0, you get 0 here for this factor, because the only number cubed that you, well, let me write it. I'm doing x cubed equals 0. The only answer there is that. And then here, all I have to do is set the x plus 1 to 0, and I get x is -1. So these are my two x-intercepts. Does that make sense? Everyone understand that? What is the multiplicity now? So let's look at the 0, this one right here. What is the power of the factor it comes from? Odd, right? 3, that's odd. What does odd tell us we're going to do here then? Cross?
And across.
Yeah, cross. And then for this one, for -1, we look at the power of that factor. That's why this step was so important. The power of that factor is 2. And that's an even number. And that means we're going to bounce here. And that should be everything I need to draw it. I'm going to try and squeeze this picture in right here. I have two x-intercepts, one at 0, one at -1. I know that my left side goes down. I know my right side goes up. And now I just need to connect this together with a smooth curve that at -1 will bounce and that at 0 will cross. So when I draw this, notice I'm going to come up to -1, I'm going to bounce off the x-axis. Then I'm going to come over here and I'm going to cross through at 0 and connect through there, and that should be it. Okay. So what I want you to do for homework is not what is in the packet, okay? Here's what I want you to do. It's going to be these problems right here. I hope you can read those. You know what? Hold on. This is actually not all of them. It's those right there. So can you all read that? I can send that to you also. But see about, you take a picture with your phone or you can do a screenshot or something, but those are the problems I want you to do. And I will warn you ahead of time that 35 and 36, when you set those equal to 0 for step 2 and you factor, you're going to need to do factoring by grouping, which we haven't done a lot of. So if you just do 31, 32, 33, 34, that's fine. You should be able to do those just with the factoring you know already. But 35 and 36, we can talk about those next class. All right. If you have issues with them. I'm not going to collect this. This is just purely for your own benefit. Do the homework. We can come back on Tuesday and I can answer questions, and we'll continue. We'll do a few more examples and we'll move on to rational functions. Any questions? Okay. Once you get those copied down, you're free to go. Have a good weekend.
Hi, thank you.
Have a good